50 years ago, the world collectively held its breath as Apollo 11 landed man on the moon. Today, I'm joined by Pat Norris, a Fellow of the Royal Institute of Navigation and Manager of Apollo Navigation at TRW in Houston from 1967 to 1970.
Gate forward. 10 and 50 feet down at 4. 33.5 down. They're pegged on horizontal velocity. 10 feet down, 3.5. 47 forward.
I guess the other major navigation issue I got involved in was I found particularly interesting was on Apollo 8, which took place in December, Christmas 1968. It was an exciting mission for many reasons. It was the first time the Saturn V had flown with humans on it. It was the first time that that humans had left the Earth's orbit and gone out beyond about 1,200 kilometers. So there were a lot of firsts, but from a navigation point of view, the main problem was that on the way out to the moon, we discovered that the radar data from 4 of the NASA ground stations was in error, was showing errors. That wasn't a showstopper in that they had about a dozen stations all told, so the other stations were sufficient to continue the Apollo 8 mission. It would not be the case. That would not have been true perhaps for Apollo 11. And so I was given the job to try and sort out what had happened. We realized pretty quickly that the problem was one of longitude, a well-known problem for navigators, in that the 4 stations were islands in the middle of the ocean: Hawaii, Ascension Island, Guam, and Canary Island. And although John Harrison had sorted out longitude, we thought, a couple of hundred years earlier, it was still quite plausible to have errors of 100 or 200 meters in the longitude of a point in the middle of the ocean. And that was the kind of order of magnitude we were looking at here, maybe up to 300 meters in one case. So after the mission was over for the next 2 or 3 months, my little team worked on calculating the appropriate longitude values for the stations. What we did was to analyze the data from previous missions to the moon, unmanned missions to the moon and to Mars and to away from the Earth into deep space. And in each case we worked out the longitude of those island stations in comparison with the stations which were well known, the ones on the continents. And we provided those appropriate numbers, the new longitude values, to NASA in about March '69, so that was in time to be used for Apollo 10. And on Apollo 10 they were used, and the radar data was fine. All the stations were fully consistent, and all of the data from all of them could be used. So NASA was kind enough to then award me the Apollo Individual Achievement Award for having accomplished that. Although, to be honest, I was more chuffed really to have had the opportunity to add a kind of a small footnote to the John Harrison story of determining longitude on a global basis. Of course, Apollo 8 itself, looking back to the mission, was a great success. Had a huge public impact. It showed that clearly that the United States was well ahead of the Soviet Union in the race to the moon, with the first humans out to the moon, into lunar orbit, and then the famous photographs of the Earth rising above the moon, so-called Earthrise photographs, which captured the imagination of a generation of environmentalists, showing the fragility of the Earth, its unique position in the universe. Now, the Apollo 11, as we mentioned, Apollo 11 was 5 or 6 kilometers. It overshot its landing site by 5 or 6 kilometers. And that had already been evident to mission controllers half an hour before the landing, because as the lunar module came around the moon, came out from behind the moon, so emerged into radio contact with Earth for the last time, half an hour from touchdown. It arrived early, a few seconds early. Might have arrived late, a few seconds late. The fact that it was early meant it was going to overshoot. It got ahead of itself. So some clever NASA people, and I can claim no part in this, they realized that by turning that early or late time into a distance and then adjusting the location of the landing site in the lunar module's computer, you could get rid of most of the error. And so that's what they did on the next mission, Apollo 12. As the lunar module came around the moon for the last time, half an hour from landing, it wasn't again, it was early by a similar amount, a few seconds. Houston worked out what that was in feet, radioed that number, single number, 4-digit number, up to the astronauts who keyed it into the computer. It was under the parameter name Noun 69. And lo and behold, they landed bang on target. It was demonstrated irrefutably that they were on target because the target was an unmanned spacecraft that had landed there 2 years previously, Surveyor 3, and they landed 200 meters away from Surveyor 3. And there are lots of nice photographs of the astronauts at Surveyor 3 with their lunar module in the background. So that rather simple engineering fix, rather than some complex mathematical one, proved adequate, and from then on, for the rest of the Apollo missions, that was deemed sufficient to undertake more ambitious missions into areas of the moon that were less forgiving, less flat, in other words, in hilly regions where precision navigation was essential in order to survive.
P64. That's it, there's LPD. Roger, copy, P64. 1000 update. Hey, there it is. There it is. Son of a gun, right down the middle of the road. Outstanding, 42 degrees, Pete. Hey, it's targeted right for the center of the crater. Look out there. I can't believe it. Amazing. Fantastic.
Apollo 12 demonstrated that you could navigate to within a few tens of meters of where you wanted to get to with this relatively simple navigational fix. In some ways, Apollo 12 almost got too close to its target. The lunar module pilot had to divert his landing slightly away from Surveyor 3. There was a danger that he would land almost on top of it. So in a sense, the navigation became essentially as good as it needed to be, at least for targets in not too far from the equator of the moon. I think if NASA had tried to go towards the poles, further than say 30, 40 degrees away from the equator, there might have been more problems. But by staying close to the equatorial regions, the fix they used of correcting the time of emergence from behind the moon, using that to correct it, the trajectory was sufficient for all the later missions. So buoyed with confidence after Apollo 12, when they landed bang on the money, the later missions went into some very mountainous regions, and of course these were of more interest to the scientists, to the geologists, and they were also more dramatic, more beautiful. They gave rise to some wonderful photographic scenes. The final mission in particular, they landed very close to very high mountains with some very large boulders, and there's some really truly dramatic pictures of the astronauts standing beside these huge boulders and crevices and mountains. So in the end, the navigation was more than good enough to provide access to whichever part of the moon they were otherwise capable of going to. They took a rover with them on the later missions, the last 3 missions, which gave the astronauts more leeway to travel around. The final mission, they drove 17 kilometers and picked up samples from a wider region, which was of more interest to the scientists. But that didn't require any complicated navigation. They were able to stay pretty much within line of sight of their lunar module. After the Apollo missions ended, so in 1972, there wasn't much research done on the moon's gravity field for about 20 years. And then in the 1990s, people started to get interested again. NASA and also some other countries sent robotic probes to the moon, and they placed them in orbits that traversed parts of the moon that had not previously been looked at. So they were in polar orbits, which gradually saw every part of the moon's surface. Their primary mission tended to be mapping. They took high resolution images of the moon's surface, but that, as a secondary consequence, allowed scientists to work out the gravity field right across the moon's surface, at least on the front side. And so with modern day computers, that voluminous amount of data, tracking data from all those missions, allowed us to work out a comprehensive gravity field formulation for the moon. It still wasn't perfect for the far side of the moon, where we did not have direct measurements, but it was good enough. The front side measurements provided enough information about the gravity also on the far side that it would have been adequate to undertake missions like the Apollo missions. And then in 2012, NASA placed the twin Grail satellites, two satellites, small satellites, into orbit around the moon, and they were designed to measure their separation, how far they were apart, and they could do that on the far side of the moon just as well as on the front side. And on the far side, they would record on board the distance their companion was from them, and when they returned to the front side, they would radio that information down to the Earth. So in that way, we got information about the very fine detail of the gravity field on the far side of the moon, as well as on the front side. And those two together, plus the data from the earlier missions, has now resulted in gravity maps of the moon, which are as good as you could need, as good as possible, both front side and back side. And perhaps as a demonstration of that, or to illustrate that, the Chinese have now landed a probe, an unmanned probe, on the far side of the moon called Chang'e 4, carrying on it a small rover, Yutu-2, which is now traversing the area around the lander. It landed in January 2019, and 6 months later it's still working, which is a major achievement. The moon is not an easy place to survive on, with 2-week-long nights and 2-week-long days. Very, very harsh environment. Anyway, the far side is proving to be just as interesting as the front side scientifically, and I'm sure there'll be many more missions to the far side now that we have the confidence and that we've seen that it can be done.